Welcome to the deep dive. Today, we're diving into the world of PCIe scaled flow control. PCIe, that's the data superhighway inside our computers. And with all the data flying around these days, keeping everything moving smoothly, that's got to take some seriously clever engineering, right?
It really does. You can kind of think of flow control as the traffic management system for all that data, making sure it gets where it needs to go without, causing any collisions.
Okay, yeah, that makes sense. So I know the system uses these things called credits to manage all that flow, but I've always wondered, how does that actually prevent those data bottlenecks?
It all comes down to communication, really, and careful allocation. So the receiving device, it issues these credits to the sender. It's basically like saying, hey, I've got this much space in my buffer, so you can send me this much data. That back and forth, that constant communication, it prevents the sender from overwhelming the receiver. And that makes sure that the flow of information is smooth and reliable, which is, it's really important because PCIe isn't just moving one type of data.
Right.
There's memory writes, there's reads, different types of requests and completions. Each of those needs its own set of credits to, make sure that one type of traffic isn't hogging the entire highway.
Ah, okay. So it's like having different lanes for different types of vehicles. That makes sense. But what happens when we start talking about massive data transfers, things like high definition video or complex AI algorithms? How does this credit system scale to meet those kinds of demands?
Yeah, that's a great question. And that's where scaled flow control really comes into play. See, before PCIe 3.0, each credit, it represented a single fixed unit of data. And that worked okay for a while when data rates were lower. But as speeds increased, it created a bottleneck. Imagine like a bus with only a certain number of seats. You can only transport so many passengers at a time, right?
Yeah, totally.
So with scaled flow control, they basically, they invented a bigger bus. Now a single credit can represent multiple data units.
Yeah.
That scaling factor, that's what it's called. And that lets much larger chunks of data be transferred with each credit, which drastically improves efficiency. It was a real game changer back in PCIe 3.0, enabling it to handle these massive data flows that we see in modern applications.
Wow. Okay. So less overhead, more efficiency. It's like upgrading to a high-speed rail line. But what I'm really curious about is how does the scaling actually happen? How does the system know when to send these scaled credits?
Okay. Well, think of it like traffic signals on that high-speed rail line we were talking about. There are two main mechanisms here. We've got credit return and implicit credit return. So with credit return, the receiver explicitly tells the sender how much buffer space it has available. And this happens periodically or when there's a big change in available space. Very direct, keeps everything in sync.
Oh, okay. So that's like the receiver saying, all clear, send the next train. But you also mentioned this other mechanism, this implicit credit return. So what's that about?
Yeah, so implicit credit return, it's a little more subtle. It's when the sender receives confirmation that a data packet has arrived safely, so then it just assumes that buffer space has freed up on the receiver's end, and then the credits that are associated with that data, they're just implicitly returned to the sender, without needing a direct message. It's kind of like a train automatically departing once the platform is clear.
That's super efficient, but I imagine there must be a lot of behind-the-scenes negotiation to get this whole system running smoothly, right?
Absolutely. So before any data transfer can even begin, the sender and receiver, they have this little handshake where they determine the scaling factors and credit limits for each type of traffic. It's essentially setting the ground rules, agreeing on how many passengers each data train can actually carry.
Right.
And it gets even more granular than that. There are parameters like furl limit, that's the perceived credit limit, and then tech consumed, the number of transmit credits that have been used. And these provide a really fine level of control over the data flow. And that allows system designers to really optimize performance for specific applications, which is pretty cool.
So by manipulating those parameters, you could potentially improve the performance of, I don't know, things like video editing software or even the speed of AI calculations?
Exactly. It's all about finding, that sweet spot for each application to maximize data throughput and efficiency.
Yeah.
Yeah, it's like having this high performance engine.
Yeah.
And, every component needs to be working together in perfect harmony.
Yeah, I totally get that. But, PCIe, it also has these other features, right? Like virtual channels and quality of service. And I'm kind of curious, how does scaled flow control interact with those? It seems like things could get, pretty complicated pretty quickly.
Well, you've got virtual channels or VCs, and they allow for different types of traffic to be separated, and prioritized. So imagine like having these express lanes on that high-speed rail line that we were talking about.
Okay, yeah.
Each VC, it gets its own like dedicated track, right?
Yeah.
And its own set of flow control credits. So that makes sure that high priority traffic, it gets the express treatment while other data, it travels on the regular lines.
Okay, so it's like a multi-level rail system then, with different trains running on different tracks, all managed by this intricate system of signals and credits, huh?
Right.
Okay, so what about quality of service? How does that fit into all of this?
Well, quality service, or QoS, it adds, another layer of sophistication.
Yeah.
You can think of it as a system for dynamically adjusting the priority of, different types of data. Like if you're streaming a movie, right?
Right.
But you're also downloading a large file at the same time.
Mm.
QoS can make sure that movie, it gets priority. So you don't experience, like, buffering or lag.
Makes sense.
And what's really impressive is how well scaled flow control works in harmony with QoS. It ensures that the right amount of credits are allocated to each traffic type, based on its priority level.
So even with all of these different layers of complexity, scaled flow control is like keeping the entire system running smoothly, huh?
Right.
I have to imagine, though, that integrating a new feature like this, that couldn't have been easy. Were there any major challenges during the development of scaled flow control?
Oh, it definitely wasn't a walk in the park.
Yeah.
One challenge was making sure that scaled flow control played nicely with existing features, like lane margining. Lane margining, it's all about determining, how much headroom each lane has, how close it is to its operational limits. And this information is used to optimize performance and reliability. But it required some pretty clever coordination with scaled flow control, to avoid conflicts and performance degradation. Like imagine trying to add a new signaling system to our high-speed rail, but without, disrupting the existing train schedules.
Right. Yeah, that sounds pretty complicated.
It was quite a feat of engineering.
But clearly they figured it out because PCIe is now capable of handling, just incredible amounts of data, and it's all thanks to scaled flow control. But the innovation doesn't stop there, right? You mentioned PCI 6.0 earlier. So what advancements does that bring to the table?
Yeah, so PCIe 6.0, it introduces this even more efficient mechanism. It's called shared flow control credits. And think of it this way, okay? Instead of each VC having its own dedicated pool of credits, there's now a shared pool that they can tap into when needed.
Okay, so if one VC runs out of credits, it can kind of borrow from the shared pool, and that prevents it from being held back.
Exactly. This shared pool of credits, it optimizes resource utilization, and it prevents any one VC from hogging all the bandwidth. It also has some other really significant benefits. Like, for instance, it reduces the amount of buffer space that's needed on devices, which lowers manufacturing costs.
Yeah.
And it can actually help prevent deadlock situations, where two or more VCs, they end up stuck waiting for each other to release credit.
Oh, wow. Okay. So shared flow control credits, it's kind of like having this reserve of train cars that can be dynamically allocated to different routes as needed.
That's a great way to put it.
That's brilliant. It sounds like a win-win for both performance and efficiency. But with all this talk about, complex technical concepts, it's easy to lose sight of the bigger picture, right? So how does all of this impact our everyday computing experiences?
Well, it's kind of, it's the unsung hero behind so many things that we just take for granted. Like, think about the high performance GPUs that power modern gaming and graphics rendering. They rely heavily on scaled flow control to handle those enormous data streams that are required for creating realistic visuals and stuff.
So the next time I'm blown away by the graphics in a video game, I can thank scaled flow control for making it possible.
Exactly. And it's not just about, gaming. NVMe SSDs, which have made storage speeds blazing fast, they also depend on scaled flow control.
Oh, right. Yeah, that explains why my computer boots up so much faster now.
Yeah.
I'm guessing this technology is also crucial for things like high-speed networking.
You got it. Network interface cards, or NICs, they use scaled flow control to ensure that those data packets are flowing smoothly between your computer and the internet. And that enables, high-speed, low-latency connections.
Sure.
Basically anything that involves moving large amounts of data, quickly and reliably, it benefits from this technology.
Wow. It's amazing to think that something so seemingly technical has such a direct impact on our everyday digital lives, you know?
It really is.
But before we move on, I have one more question. You mentioned TCP/IP earlier, and that's the protocol that governs internet communication, right?
Right.
So does it use flow control too? And if so, how does it compare to what we see in PCIe?
That's a great question. So both PCIe and TCP/IP, they use flow control, but their approaches differ in several key ways. PCIe, as we've discussed, it relies on this credit-based system, and those credits, they represent buffer space at the receiver, right? And that credit size, it's variable. It can be scaled to accommodate those high data rates. TCP, on the other hand, it generally uses a fixed window size for flow control. So the sender can only transmit a certain amount of data before it has to wait for an acknowledgement from the receiver.
Oh, okay. So with TCP, there's like a limit on how much data can be in transit, at any given time.
That's right. And this fixed window size, it can become a bottleneck for high-speed networks, where large amounts of data need to be transferred quickly. Another key difference is how they handle credit returns. So PCIe, it supports both explicit credit return, where the receiver directly informs the sender about, available buffer space, and then implicit credit return, where credits are automatically returned upon successful data packet reception. TCP primarily relies on explicit acknowledgments for flow control.
So PCIe offers more flexibility and efficiency in managing credit returns then?
Exactly. And there's one more key distinction. It's granularity. So PCIe flow control, it operates at a much finer level of granularity. It manages credits per packet type, like posted, non-posted, and completion packets. And this allows for more precise control over those different types of traffic. TCP flow control, on the other hand, it typically operates at the connection level. So it's managing the overall data flow between two endpoints.
Oh, okay. It seems like PCIe scaled flow control is specifically designed to handle the demanding requirements of high-speed data transfers within a computer system then. Like it's like a finely tuned orchestra, compared to a simpler musical ensemble.
Yeah, that's a great analogy, and it really highlights why scaled flow control has become such a critical technology in modern computing.
Yeah, it's really incredible how much complexity goes into something that, most people never even think about.
It really is.
Yeah.
It's a real testament to the ingenuity of the engineers who are constantly pushing the boundaries of what's possible. And it reminds us that even though technology can seem really complex, it's ultimately about solving real world problems, right?
Yeah.
And improving our lives.
Absolutely. So for our listener who may be, just starting to grasp the importance of this technology, what's the key takeaway here? Why should they care about PCI scaled flow control?
Well, whether they realize it or not, it's impacting their digital experience every single day.
Yeah.
Things like streaming a movie, editing videos, browsing the web, all of these things, they rely on this smooth and efficient flow of data.
All right. Yeah.
And that's made possible by scaled flow control.
So like the unsung hero, working tirelessly behind the scenes to make sure that our digital lives run smoothly.
Precisely.
Yeah.
And as we move towards an even more data-driven world, with the rise of AI, the Internet of Things, and all these other bandwidth-intensive applications, the importance of efficient flow control, it's only going to grow.
That's a really good point. So the next time our listener's computer is, downloading a massive file or rendering a complex 3D model, they can take a moment to appreciate the intricate dance of credits and data packets that's making it all happen,
Right.
seamlessly.
Yeah. And if they're curious to learn more, there's a whole world of information out there just waiting to be explored. Perhaps this deep dive has sparked an interest in the inner workings of their devices.
That's what we hope for. There's always something new to discover. And who knows, maybe someday our listener will be the one designing the next generation of flow control technology.
The future of computing is full of, exciting possibilities.
Absolutely. Well, that brings us to the end of our deep dive into PCIe scaled flow control. We hope you found it insightful and engaging.
Thanks for joining us.
And remember to subscribe to the deep dive for more explorations of the fascinating technologies that shape our world.